So we're going to talk about sound waves today. I want to first start off by saying a sound wave is a longitudinal wave. So what we can expect with that is if we were able to see the air molecules, we would see them compressed, then stretched out, and then compressed because it is a longitudinal wave. In general, what you could say is going from compression to compression. That's the wavelength of the wave, um, and so on and so forth. So sound waves can travel through pretty much anything, solid, liquid, and gas. Some materials it travels more effectively than others. Um, and the speed in which sound travels also changes quite dramatically from medium to medium. These solid, liquid, gas, we call these things mediums. So it could be air, it could be water, it could be salt water, it could be metal, it could be a brick wall, it could be drywall, etc. Let's start with a simple problem. Let's imagine here's a big storm cloud, and boom, there's a lightning bolt. And way off in the distance is you. And you see the flash, but there's a time delay, say 7 seconds before you hear the boom from the thunder. So that sound wave takes an entire 7 seconds to finally reach you. The speed of sound in air is 343 meters per second. That's 343 at standard temperature and pressure. We're not going to deal with what happens if the atmospheric pressure changes or the temperature changes. We're just going to stick with 343 for air. Velocity is distance over time. So 343 equals the distance that sound wave traveled over the 7 seconds that it was in motion. So we do 343 by 7, and you get 2401 meters, which is about a mile and a half. So every 7 seconds that passes after you see a lightning flash, and you count to 7 before the boom, mile and a half. So another principle of sound waves is their ability to echo. And what's happening in an echo, if we imagine we have a pet dolphin, which I'm going to do my best to draw our pet dolphin. It's some kind of aquatic creature. Here's our dolphin, and he's hunting for some fish, so put some goldfish in the water for him to go find and eat. Now, the dolphin uses echolocation. It has much more complex auditory system in its brain, which allows it to basically use sound in a similar way that we use sight. Now, as it squeaks, the sound wave leaves the dolphin. Parts of that sound wave bounce off the fish. And when they bounce off the fish, they're going to return to the dolphin. So let's say our dolphin is very sophisticated and knows some mathematics. The speed of sound in water is about 1,500 meters per second. Let's say our dolphin squeaks, and 3 seconds later, he hears a squeak again. So velocity is distance over time. We would say 1,500 is the distance over 3. In conclusion, the distance is 4,500 meters. This is the first mistake that people make when dealing with echo is they want to say that the dolphin is 4,500 meters away from dinner. That is false. What we just calculated was how far the wave traveled. So the wave traveled here, hit the fish, and came back. So we have to take our 4,500 and cut it in half. Doing so gives us 2,250 meters. That's how far away dinner is. Human hearing, since we are talking about sound, it makes sense to discuss human hearing. It is 20 hertz to 20,000 hertz on average at birth. Your lower level stays pretty constant throughout your life. That one doesn't really change. And it also doesn't really matter because things around 20 hertz, we don't really hear many items around 20 hertz. This one decays as you age. On average, it tends to decay earlier in men than women, but don't let that be an excuse for why grandpa couldn't hear whatever grandma said to him. Because although it decays, Human speech is around 400 to 1000 hertz, and that upper level never gets close to 1000. Me, for example, at age 34, my cutoff is around 15,000 hertz, and I get through my everyday life just fine. Uh, you, as teenagers, you're probably around 18 to 19,000. To the male students listening to this, your hearing is going to start its decay process shortly after you physically peak, so around 18, 19 years old. This number is going to start going. Typically, in women, you get to hold on to it until your 30s before that one starts to go. It's not going to really change your life because nothing is really that high pitch. Uh, your fluffy puppy, for example, though, can hear up to 30,000 hertz. That's effectively how a dog whistle works. We can't hear it because the frequency is way too high. Another phenomenon is known as beats. And what beats are, I'm actually going to go into this and play some beats for you. If we see here 500 hertz and 500 hertz, I hit play and I'll stop it so that way it doesn't get really annoying. You heard a constant tone. But if I go ahead and change this to 500 and 501, you may think, well, 1 hertz, is it really going to make a difference? What about 500 and 502? Make it 505. You're getting this wah, 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 wah sound. Those are beats. What's happening is the waves are slightly out of tune, and we can actually calculate the beat frequency simply by saying what was the difference in the beats, F1 minus F2. So in this case, 500 minus 505. Put them in absolute values. It doesn't matter which number is bigger than the other. The point is, you're going to hear 5 beats. That means you're going to that whoa, 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 whoa sound. You'll hear it 5 times in 1 second. This is what they talk about in music when they say one of the musicians is out of tune. Let's say you are in an orchestra and 3 violins are supposed to be drawing the bow such that they're all supposed to be producing 500 hertz. But in the process of doing so, you end up getting some whoa, 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 whoa type sounds. This is because at least one of the violins is out of tune. In order to change that, the violinist can either tighten or loosen the string, usually tighten the string, in order to get themselves back in tune. Sound intensity is measured on the decibel scale. So, decibels, I believe it's decibels. Not sure on the spelling on this. Yeah. So, that doesn't really matter. What does matter is that you know it's a logarithmic scale in nature. So, what do I mean by logarithmic scale? 10, 20, 30, 40 decibels. Whispering is around 40 decibels, conversations around 50 to 60 decibels. As we get higher and higher, now we're at like vacuum cleaners, lawnmowers. At around 120, you're at the threshold of pain. The threshold of pain is defined as a point in which if you hear that sound, there's permanent, irreversible damage done to your ears. But now, the term that I said a moment ago was it was logarithmic in nature, or it's a log-based scale. So let's take, for example, if I want to go from 40 to 80, one might think, all right, going 40 to 80, that's twice as intense. That's false. It's a log scale, so it's 1, 2, 3, 4. People are going to start saying 4 times as intense? Not quite. 10 to the 4th, or 10,000 times as intense. Why 10,000? Because to go from 40 to 80, I stepped up 1, 2, 3, 4 times. So 1, 2, 3, 4 zeros. So there is a huge difference between a gentle whisper down here versus, say, a jet aircraft taking off up here. The next piece is the Doppler effect. So the Doppler effect works on this idea of squishing the waves. Let's take a cop car here. It's quite the drawing, but it works. And our car is stationary. Velocity of this vehicle is 0. So let's think about what happens. Well, the cop car is continuously generating sound waves. So here's a sound wave, here's a sound wave, and here's one more big sound wave. Okay? And these sound waves are equal distant. Now, let's run through what happens if our cop car starts to move. So, you have the police car. Whoops. Well, this is frustrating. There we go. Okay, sorry about that. So, you have the police car moving to the right. Now, let's say that orange wave is generated. Here's the orange wave. Okay. And what I'm going to do is I'm going to put a red X right here. The red X does not move. The cop car does. A brief moment later, our cop car, here's that red X once again. Our cop car has moved over here. Siren still blaring. This orange wave has expanded, but it's still centrally focused on the red X. Now, another wave is emitted from the cop car. Notice what's happened. This is compressed on the front end, and this is stretched on the back end. This is effectively what the Doppler effect does. It's a compression and stretching of sound waves because either the source of sound is moving or the observer is moving. The truth is the waves are maintaining the same frequency as far as the police officer inside the cop car is concerned. He keeps hearing the siren, the same frequency, the frequency it's supposed to be at all times, because he is moving at the exact same speed as the sound. Now, to somebody standing on the road here, they're going to hear a high pitch. What happens is the wavelength is decreased, the wavelength being the physical distance between these waves. The thing is, though, the speed of sound in air is a constant 343. So the result is the frequency increases. So you hear a high pitch wailing sound. On the backside, somebody who's watching the cop car drive down the road and it's already past them, these waves are stretched out. So the wavelength has increased under constant speed, causing the frequency to decrease. The very last thing to talk about with sound is resonance. And it's not just sound, but it's all waves in general. Best way I can describe resonance to you is what you're going to do is you're going to go ahead and think about pushing your niece or nephew on the swing. So here's your kiddo, pushing them on a swing on the playground because you're a good aunt or uncle. Now, you stand behind them and push. Now, let's think about how you're pushing them. You do not apply a constant force. You push and wait. Push and wait. Push and wait. What do? They swing. And The only time you exert a force as they swing back and forth, back and forth, back and forth, you only exert a force, boom, right here. The child is effectively a pendulum, back and forth. That's one cycle. Swing forward, swing back. One cycle. Swing forward, swing back. Two cycle. Swing forward, swing back. Three cycle. What you do is you push and wait. Push and wait. Push and wait. What has occurred is you exert a force in cycles. The timing of your force and their completion of a cycle is the same. You apply a periodic force. The frequency at which you apply your force is the frequency at which the child completes cycles. So you've matched their frequency. This effect is known as resonance. When you cause resonance in an instrument, that's what causes the instrument to make a constant sound. Whether it's drawing a bow across a string on a violin, or if it's blowing air through a column such as a flute or a clarinet or a trumpet. That effectively is resonance. It's a periodic force that's applied to an object, and the period or frequency of the force is the same as the frequency of the object. You can look up something if you're really curious called the Tacoma Narrows Bridge. So, what happened a long time ago in the 1940s is somebody wanted to build a suspension bridge in order to get from point A to point B. Makes sense. There was a way to get from point A to point B without the bridge. The problem is it was one heck of a long drive. Now, suspension bridges are called suspension bridges just for that reason. They suspend the bridge. You put two towers into the bedrock of the lake, river, whatever it happens to be, and then here you secure a cable, and you take that cable, bring it up, secure it to a tower, secure it to the next tower, secure it to the other side. You do this on both sides. To save in the drawing, I'm just going to do it on one side for right now. Then what you're going to do is you're going to hang cables from this. So we hang them, hang them, hang them. After you've hung these cables, you're going to then take your bridge in sections and connect it. Hence the term suspension bridge. You obviously do it on both sides of the bridge. I'm only drawing it on one. Now, what the bridge effectively is a very complicated child on a swing. It's a pendulum. If we think about this drawing here, but on an overhead perspective, you have water gets into this narrow channel, and we have the bridge hanging here with tower. This is land. This is land. It's higher elevation than the water. And you choose to make your bridge at a narrow gap within the river, within the lake, whatever. Notice the Mackinac Bridge is in the Mackinac Straits. It's only 5 miles long. We're not going to build a suspension bridge from Michigan to Wisconsin. It's far too long. What happens, though, is as air is moving into this channel, it gets compressed. And these gusts of wind can begin acting like a periodic force. In doing so, it will apply force onto the suspension bridge. This is normal. That's why suspension bridges can swing They don't swing very fast. It's very slow. You don't really notice it when you're on the bridge itself. If, however, you just happen to build a bridge that has the same natural frequency, because, like I said, the bridge is technically a pendulum, if that bridge happens to have the same natural frequency at which these gusts of wind are blowing through the channel, well, you cause your bridge to resonate. So, if you're curious, I recommend looking up the Tacoma Narrows Bridge, and you'll be in for a rather fascinating video. All right, the next video for today is going to be going through the worksheet on solving some math problems.